Continuing on with a discussion about parallel streams and internals, we're now going to talk about how the parallel streams abstractions, the functional programming abstractions, get mapped onto the common fork join pool. And once again, we're not going to cover fork join pool in all of its full-blown glory. We're just going to cover enough of it so you can understand how it's used as the basis for the parallel processing engine in the context of the parallel streams framework and the completable futures framework. So I'm going to show you how the parallel streams elements are mapped onto the common fork join pool. So the first thing to remember, or first thing to know about the fork join pool, or the common fork join pool, is that it has a bunch of worker threads, and by default, there are typically as many worker threads as the Java execution environment thinks there are processor cores on your hardware device. So let's say, for sake of argument, that we're running on my MacBook Pro, which has 8 hyper-threaded cores, which is basically 16 logical cores. So the execution environment, the virtual machine that is running on my MacBook Pro thinks that there's 16 cores. So we'll let it live in its delusion, but that's what it thinks. And therefore, it's going to spawn a certain number of worker threads. We'll see exactly how many shortly, but there's a bunch of them. And each of these worker threads is a Java thread, and it basically spends each Java thread in the worker thread pool, spends its entire life cycle running a loop, scanning for tasks to run. So just think of it like running in a hamster wheel or something like that. In this particular discussion, we're only going to focus on how this is used for parallel streams. There's obviously other ways you can use it if you're programming to fork join pool natively. Keep in mind that the goal of all this is to keep the worker threads and the underlying processor cores, of course, as busy as possible. We do not want these things to stop for a moment if there is work to do. Now, the way this works under the hood is each worker thread that's in the common fork join pool has a double-ended queue, which is known as a DEC. It's pronounced DEC, not DQ, but DEC, that serves as that worker thread's main source of tasks to process. And the parallel streams framework, particularly the splitterator that is being used in a given stream, creates fork join tasks while the splitterator process is running, and then passes them off to the common fork join pool where they're going to be run by worker threads. So that's how work gets into the common fork join pool. It gets split up by the splitterator, which is partitioning the data source up into chunks, and then those get passed off to the thread or threads in the fork join pool. If you were to take a look at the source code for Java streams, you would find there's a file called AbstractTask.java, and in it, it has a class called AbstractTask. And this is a superclass that most fork join tasks use to implement the parallel streams framework. And so you can see here that an abstract task is used to manage the splitting logic, the tracking of child tasks, and also the handling of any intermediate results as the stream is running. Abstract task is a task in the sense of the fork join framework, and therefore it has a method called compute. And compute is used, as we'll see in a moment, to decide whether to split a task up further because it's still bigger than some min size, or to compute it directly. So that's what compute has to do. That's its purpose in life. And the way it works, as you can see here, is it's actually going to take the splitterator that's defined for a parallel stream, and it's going to keep calling its try split helper method. Remember, this is the streams framework. This is the parallel streams framework doing this, not your application code. This is the streams framework. And it's going to keep calling try split until try split finally returns null. And you guys had experience with this when you wrote your program where you had to do the splitterator, the array splitterator for the unsynchronized array. And you remember that you had a try split method and a try advance method. So the try split method here is called by the framework until it finally says, "Uncle, I give up, can't split things any further." And every time it splits, you end up with that going into another splitterator. So you have the RS for the right-hand side splitterator and LS for the left-hand side splitterator. and we keep splitting until we don't have anything left to split. Now, what happens here once we've finally reached a point where every time we get something that's not null, every time we're able to do a successful split, we're going to go ahead and decide if we're going to be forking the left child first or the right child first. And this is just done to avoid biased splitterators, where you end up traversing down one side of the tree, one side of the splitterator tree to the exclusion of anything else. So in this case, it just goes back and forth. It just alternates. Sometimes it goes left side, sometimes it goes right side. No matter which is chosen, we figure out which task is going to be forked, and then we fork the task, or rather the framework forks the task. And what that does is it makes a new subtasks and then continues to process the other task in the loop, in the caller. So the way the ForkJoin framework works is you typically fork one half, and then you take the current thread and run the compute method in that. So you don't actually end up forking twice for the left child and the right child. You fork for one side, give that off to potentially to a new thread, and then continue doing the processing in the current thread. When try-split finally returns null, when we've reached the end of splitting and there's nothing left, it then calls the do-leaf method on the task. And what this does is it will end up calling for each remaining, and then that will in turn end up calling try advance. So that's how the try advance hook method gets called. And the try advance hook method gets called back on a splitterator once you can no longer subdivide the source at that point any smaller. So at that point, then you go ahead and call try advance. And so that's how those hook methods get called on the splitterators that you may define or that come predefined out of the box by Java. So whenever the compute method calls fork on a task, as we saw here, back here, it calls fork. Here's what happens. That task is then pushed onto the head of the queue or the deck that the worker thread happens to have as a consequence of being the current thread that's doing the processing. This may be a little confusing at first, but what's happening here is that there's a pool of threads. Those threads are part of the system. That's the common ForkJoin pool. And that pool of threads, one of those threads in that pool is going to be doing the AbstractTask compute method. And it's going to go ahead and call fork. And then that will go ahead and queue up that task in that worker thread's deck. So what happens when fork is called, and ends up pushing the task onto the head of the deck. So it'll be the next one to be processed. Each worker thread, remember each job, whenever I say worker thread, I mean a Java thread, processes its deck in LIFO order, which is basically stack discipline, last in, first out. And so what that means is when it's time for the thread to do some work, it'll pop the item off the stack, off the deck, and then it'll run it. So the most recently inserted item, or the most recently pushed item, will be the one that is popped next. When a thread is popped, when a task is popped off a deck, it's then run to completion. And what that means is it'll just keep running until it's done. Now, it might also block in some situations if it happens to need to do I/O, or it needs to wait for some kind of synchronizer, or it has some other coordination step that's required. But the point is that it'll just keep running until it's done. So the reason why LIFO order is used for handling pushing and popping onto a deck by a worker thread is to improve locality of reference and cache performance. And the reason for this is often known as the fresh work before stale pattern. And fresh work before stale basically says things that have most recently been pushed are best to work on, because chances are the state and any instructions that may need to be run are probably still in the processor cache, the instruction cache, and so on, the data cache. And so we're more likely to be able to get a performance win if we do fresh work, the work that was most recently pushed, before we do the work that's kind of stale. It's been there for a while. So that's why the way in which a worker thread gets data off of its work queue, off of its deck, is by using LIFO processing. And I bring this up because it makes a great quiz question. So you should definitely make sure you understand why worker threads access their decks in LIFO order, access their own deck in a worker thread, access its own deck in LIFO order. Now, interestingly enough, there's this other concept that says, if I'm a worker thread and I've reached a point where there's nothing left in my work queue, in my deck. So let's say here, you can see that this work queue in the middle is empty. And so this thread here hasn't got anything else to do. Rather than blocking or just spinning idly, what it'll do is it'll go look around and then randomly steal work from the end of some other worker thread's deck where there's actually work still remaining to be done. So it may turn out, for various reasons, because of the speed of the processing or the amount of work to do or just the size of the queue or the size of the deck and so on, that some worker threads have work that they haven't gotten around to yet. And so when one worker thread finds it doesn't have anything to do, it goes and it steals work off the end of somebody else's deck. And we'll talk more about this later. But the long and the short of it is that this allows the processor, the multi-core processor, to keep all the threads, all the cores as busy as possible by stealing work when the current worker thread or a given worker thread has run out of things to do. And so that's actually how the tasks get moved around between the various worker threads in the pool, is they can be stolen. So if it turns out that one thread pushes lots of stuff onto its deck, then the other threads will start stealing from it. And then those threads in turn will have their queues stolen from by other worker threads if they're unable to process everything without having stuff left over that other threads with nothing to do need to get access to. So that's basically an overview of how the abstractions for Java parallel streams, basically the chunks that created by the splitterators, get mapped onto various worker threads in the ForkJoin pool, and then the common ForkJoin pool, and then how those threads in the common ForkJoin pool will steal work from other decks from worker threads that don't have enough to do. So if you really want to learn more about this stuff, I have other videos on my website that talk in detail about the common ForkJoin pool and the ForkJoin pool in general. But this is probably good enough to keep you moving at this point, because we don't really need to know the details of how this stuff works for parallel streams. We just have to be aware of the fact that it does exist, and therefore makes it easier for the system, the parallel streams framework, to optimize the heck out of the processing without you, the programmer, having to worry about all these low-level implementation